Welcome, everybody, to the first of what we hope is a long and continuing series of public lectures. This idea for a lecture series is a work in progress. Our current title for the series is Our Universe from the Quantum World to the Cosmos. My name is Blaine Heckel. I'm chairman of the Department of Physics. And as such, it's my privilege to welcome you here tonight. And it's also my privilege to thank Patrick and Katerina O'Hara for their generosity in making this public lecture series possible. Patrick, could you wave your hand? I don't see where you are. Thank you. Patrick had the vision of bringing the excitement of current breakthroughs in physics to an audience of non-scientists and scientists alike through this lecture series. We plan to bring out top experts across various fields 2 or 3 times a year to give these talks. The next lecture will be in about cosmology 7 weeks from now. There was one more. Our goal is to keep these lectures free of admission. And so if anyone shares Patrick's vision, you are invited to make a donation to keep this lecture series vibrant. So that's my pitch. There's always a pitch. That was it. At this point, I would like to call on Professor Xiaodong Zhu, who will introduce tonight's speaker. Professor Zhu's research is in the physics of small.
Thank you. So it's my greatest honor to introduce today's speaker, Professor Paul McEuen. First, I would apologize. The introduction might be a little long, but I think the person of guilty is not me, it's Paul, since he has achieved so much. So Paul received his bachelor's degree in engineering physics from University of Oklahoma at 1985. Then his PhD in applied physics at Yale University in 1991. So after a short stay at MIT as a postdoc, Paul became a professor at the University of California, Berkeley in 1992. Then he moved to Cornell in 2001. So Paul is a Goldwin-Smith Professor of Physics and the director of the Kavli Institute at Cornell for nanoscale science. He has received numerous awards for his research, including Office of Naval Research Young Investigator and Alfred Sloan Foundation Fellowship, National Young Investigator Award, Packard Fellowship, and the Packard Foundation Interdisciplinary Fellow, and Angeland Technology Europhysics Prize. He's also a fellow of American Physical Society and also a member of National Academy of Sciences. So Paul is known for his work in electrical and the mechanical property of carbon nanotubes, scanning probe microscopy of nanostructures, molecular electronics, and the application of nanoelectronics in chemistry and biology. Paul is not only known as a scientist, he's also a novelist. So his first scientific thriller, Sparrow, was released in 2011, in which a Cornell biology professor is murdered as part of the plot involving a biological weapon. So I love this book so much, actually I bought 2 copies. And a few years ago, I was very lucky to have Paul as my postdoc advisor. So I could not ask for any better mentor than him. He's my favorite scientist and someone I always look up to. So whenever there's a challenging situation, I always ask myself, what the Paul will do. Then the problem just disappears. So it may sound like a religion to you, but it works for me. So please join me in welcome Paul.
So thank you very much. Everyone hear me okay? Great. Okay, there we go. Now you hear me? That sounds better. First off, I just want to thank Xiaodong and also David Cobden very much for inviting me here, along with all of you for coming. I'm very excited to be talking to you tonight about I've called the future of small. It's really a talk about technology, but I should warn you, it's a talk about technology given by a physicist. That should give you pause, because physicists have kind of a strange relationship with technology. Let's, for example, think of technology as a cow. If you're from Cornell, you think of a lot of things as cows. Well, as you know, if you're a physicist, you will think of a cow as being reduced to its sheer essence, which turns out to be that it's topologically spherical, it goes moo, and it has spots. So we like to simplify things. Physicists like to reduce things to the clearest essence. But they also like to do something else. Physicists like to push things to the limits. They like to take ideas and see how far they can go before they snap. And to illustrate that, I'll use a quote by Dave Barry, who says that the physicists tell us that the fastest animal on Earth with a top speed of 120 feet per second is a cow that has been dropped out of a helicopter. So if you think that sounds like fun, dropping cows out of a helicopter, you might be a physicist. So that's going to be the spirit of the talk. We're going to talk about technologies, but we're going to talk about them in a sort of a vastly oversimplified form and see what happens if we stretch them to their limits. Okay, I'm supposed to tell you about the future of small. Well, I should start off by telling you about the past of small. And so I'm going to do that in three slides, so everything you need to know about small. We're going to start our story in 1665, which is the birthplace of small, and I'm going to identify the first father of small to be Robert Hooke. Now, if you're not a physicist, you might not know who Robert Hooke was, but he was a very famous scientist that emerged around the time the Royal Society was being founded. Hooke's law for springs, that's that Robert Hooke. There's a drawing of one of his springs down there. But he was also one of the first micro and nano people in that he took the optical microscope, which had been very recently invented, and he made a series of very detailed and careful observations of everything he could stick under the microscope, very much like a physicist would do. Everything from pictures of tiny little bugs to this thing on the right, which each little individual element of he identified as a cell. So he also was the first to coin the name cell for cells, and it was an analog to where a monk lived inside of a monastery. He thought that's what that looked like, and that was the birthplace of the word cell. He also was interested in lots of other things. He was interested in clocks. He was interested in the history of the Earth, archaeology, biology, gases, you name it. He was very interested in all this and made enormous contributions in all these fields. And you may ask, why haven't you heard more of him? And that's because one of the things he was interested in was gravity. And in fact, he was a contemporary of Isaac Newton, and they fought bitterly over the intellectual property rights to gravity, roughly speaking. That will be another theme that will emerge in the talk. And so this is the guy he fought with, Isaac Newton, who basically won. He won the battle. Isaac got credit for the inverse square law, won the war, later came on to be the head of the Royal Society, more or less did his best to purge Hooke from the name, from the memory of the place. There are rumors about stealing a painting of Hooke and disposing of it. Anyway, Newton won, and so we haven't heard so much of Hooke. But Hooke really was a hero to anybody who thinks about small, because he was the first to really look with great wonder at the world that opened up to us with the invention of a new tool, the microscope. So the invention of the microscope revealed this world that existed that nobody was aware of. All these little creatures that we would discover, bacteria, you name it, everything that he looked at that was small, he found fantastic wonder. Now, the amazing thing is, because around the same time everybody figured out gravity and started thinking about big, started thinking about planetary systems, started thinking about going to the moon, basically this idea of small got lost for a while. So the next step in the journey of small is going to jump forward to 1959. Because in the intervening few centuries, we basically forgot about small. Not entirely, but to a great extent. And I'm going to use another physicist to mark the next stage of small, which was Richard Feynman, who, as many of you probably know, was one of the most famous physicists of the last 100 years and gave, among other things, a very famous talk called There's Plenty of Room at the Bottom. And in that, he did what physicists do. He said, you know, let's just think about what would happen if I started to make things small. What would that mean? What laws of physics would I run into? What could I do if I made things small? Why not? And it's an amazing piece of work. I encourage you to go read it if you want to see a very, very clear mind engaging a very, very interesting question. But I'll boil it down to the essence of what he said. The first thing he said is, you know what? You could just miniaturize information. You could take information that was written in a book and make it smaller. And then you could put a lot more information in a tighter area. Furthermore, he said you could miniaturize computation. There were at that time computational machines around, very mechanical in nature mostly. And he said, you know, you could just shrink all that computation down and you could do information processing. And because you made it small, you could do an enormous amount in an incredibly tiny volume. And that would wildly speed up what was possible. You could store, you know, the entire Library of Congress on a coin, things like that. And of course, that was incredibly prophetic because the next chapter in the past of small, the history of small, is, you know, now we basically have done what Feynman told us to do and have created modern computers and everything that goes with them. Cell phones, lasers, the internet, the cloud, you name it, it all flowed from this idea of getting small and being able to put an enormous amount of stuff in a very, very tiny area. And it's kind of interesting because it wasn't really on people's radar screen in the late 1950s that small was the new big thing. Everybody thought atomic airplanes were the new big thing. Atomic airplanes didn't work out so well. There were some problems with the shielding, but small was the new big. I should say the journey is not over. We're still making things smaller, and I'll just mention very briefly the sort of frontiers of small in the realm of electronics, for example, is graphene. Many of you have probably heard of this. You take graphite, pencil lead, you take an atom-thick sheet of it. It looks like that cartoon that you see there. And that single isolated sheet of graphene is a very interesting electronic device. You can make transistors out of it. You can generally have fun studying it and make basically a transistor that is only one atom thick. So at least in the Z direction, it's the ultimate miniaturization. It's as far as you can get. I don't know how to make a transistor that's thinner than one atom. And this field got underway in 2004 or so and won the Nobel Prize in 2010. But it's not just graphene. I'll mention that there are lots of materials that are now being investigated at the smallest scales. One that I like, this is from my collaborators at Cornell, David Muller's group. So this, what you're seeing there, that picture there, that's an image taken in a new fancy microscope, this case an electron microscope, which can go down and see individual atoms in a two-dimensional material. And so what you see, that network of little lattices, that's basically a monolayer of glass. That's the thinnest possible window pane you could ever make in the world. And in fact, it made it into the Guinness Book of World Records in 2014, no small feat, along with a goat that set the world's record for skateboarding. But Pinchane was very happy when she got in there. But this also shows the evolution of the tools. Now we just don't have microscopes to see at the micron scale. We can go down and see at the angstrom scale with electron microscopes. And these two-dimensional materials are perfect for it because they're all laid out for easy viewing. And it's not just electronic materials like graphene and 2D glasses. People are also making interesting optical materials, reinventing laser physics and what have you in that world. Our own group does some work in this area. And in fact, here at the University of Washington, Xiaodong and David's groups are leading the charge to reinvent optoelectronics in these two-dimensional materials, creating lasers, diodes, you name it. And it's an extremely, extremely exciting time. Okay, so that's great, right? Except, you know, if we take the long view, not the 5-year view, but say the 50-year view, you know, we've gone as thin as you can get. I mean, are we, you know, I mean, is small almost over? Are we done? Where do we go from here? Yes, it's over, so thank you. Good night. No, it's not, and we have a place to go because all we have to do is go back and listen to Richard Feynman. If you're a physicist, when in doubt, so it's not what would Paul do, it's what would Richard do. Richard always would tell you what to do, and what Richard said to do after you do miniaturizing information and computing is Feynman said, you can also miniaturize machines. You could build nano submarines. You could build little machines that could go in your bloodstream and move around. And those of you over my age and older may recognize the nano submarine in question from the movie Fantastic Voyage. And you might say, okay, well, why would you want to miniaturize machines? What would that even look like? And to answer that question, I'm just going to show you a worked example of a world full of miniature machines, and that is, of course, you guessed it, biology. So this is an animation of what it looks like inside of you. This is zoomed in. This is made by a group at Harvard who tries to make semi-realistic versions of what's going on in biology. And if you zoom inside of a cell, you will find all kinds of jittery nanoscale machines going about their business of duplicating DNA, creating proteins, the proteins doing functions, et cetera, et cetera. It's an unbelievably amazing dance of machines doing stuff at the nanoscale. And all those machines, nobody's listening to me, I'll shut up and let you watch for a second. All right, well, I have no idea what any of that is, but it looks cool. And as a nanoscientist, I want to build that or something, not exactly that, but something like that. Because, of course, if you can make those kinds of nanomachines working together in that sort of complex fashion, you get stuff like us. And instead of needing a multi-billion-dollar factory to do your fab, well, you get the idea. It's a much more pleasant manufacturing process. So, I'm going to say, in a certain sense, the information revolution was pretty cool, but it's nothing compared to what could happen with micro and nanoscale machines. And I'm going to use a quote by Buzz Aldrin, the astronaut, this is from MIT Technology Review, where he said, "You promised me nano submarines, and instead I got Facebook." Actually, you may notice that it looks like the cover has been doctored a little bit. He actually said, "You promised me space colonies, and instead I got Facebook." But the idea is the same. The thing beneath it is really good. It says, "We've stopped solving big problems. Meet the technologists who refuse to give up." That's what we want to be. We want to be the ones that refuse to give up, and try to do big stuff. In this case, something big being something small. And to be a little more specific, what I would like to do, what would be great to do, is to be able to make nanoscale machines, or even microscale machines, that on one hand retain all of the wonderful stuff that we've learned how to do in inorganic materials, or in graphene, or in molybdenum disulfide, or what have you, make lasers, do computations that are faster than their biological equivalents, but at the same time somehow use some of the ideas and techniques, and certainly be able to shrink down to the kinds of scales that biology knows how to do stuff. So can we do something that sort of marries these two worlds together in an important way? That would be amazing. And we're not going to get there by the end of this talk. This is a 50-year goal to do something like this. It's sort of like we're kind of at the place where the semiconductor industry was in the early 1960s, where we're just starting to do stuff and dreaming of what the world is going to look like 50 years hence. Okay, so is this a good idea? Should we try to build these? I mean, well, come on, no, right? Of course, they will, any of you read Prey, they take over the world, they eat you, you're dead. So it seems like a bad idea. Do we want to even be able to make these kinds of micro and nanoscale machines? And I think, the answer is yes. And just to give you a couple of general ideas of the kinds of things you might do, let me look back in history a little bit to a technique that many of you are probably familiar with, laparoscopic surgery. Okay, in the old days when they had to do something to you, they cut you, from top to bottom and peeled you open so they could get their hands in there and do stuff. It was horrible. Then they came up with the idea of we'll just go in through little holes, but they also had to see inside. So what did they do to see? They would stick in a little tube with a little eyepiece, and they would hold their eye to the eyepiece, and they would work on you. And in fact, the limitations of doing that kind of laparoscopic surgery was basically the back of the surgeon couldn't stand like that for too long. And so the invention of the camera made laparoscopic surgery, that's why what are they all looking at? They're looking at a television screen that is tied to a camera that is showing them what's going on inside of the belly. So the information revolution gave you the first step in this. It got you to where the visual information was coming out in a much more effective way. But I mean, come on, look at those tools. That's disgusting, right? These things going through you, they look like feed-throughs in a vacuum chamber or something. We can do better than that, right? Can't we build some little robot that goes, you just make a little hole and push it in, and then it runs in and does what it needs to do? Why can't we do better? It seems like we should. And certainly it would make it much easier to recover from surgery, and you could do much more advanced surgeries. A second class of things is, very popular, the idea of the Internet of Things. We're going to not only have all this information technology, but this information technology is going to move out into the world and gather data and control things. And the Internet of Things is sort of a part of the story that I'm telling. And just to give you a few examples of things that are being thought about in various contexts. For example, many of you may have heard of Obama's BRAIN initiative that was launched about a year ago. I had a very small role to play in that process. And one of the key questions was, can we build better techniques for going into people's brains and learning about what's going on in there, or in the case of stroke victims, helping to make things go better, or paralysis victims, et cetera. But again, now what they do is roughly speaking, they take ice picks and they jam them in people's heads. That's what they do. Can we make something that's much more attractive, a way of getting in there? Can we send a nano submarine into someone's brain? Similarly, the microbiome, there's a tremendous amount of excitement in biology. The discovery that inside of, say, your stomach, there's an entire ecosystem that we don't really know very much about. All we know about it comes from basically from new genomic sequencing techniques. In a couple of weeks, I'm going to go to Washington, D.C., because there's a big movement on to try to develop new techniques for going in and being able to see sort of on the ground what's happening in the microbiome. Again, you would like to have some sort of nano submarine to do that. And finally, the most ridiculous, but therefore my favorite, is, if you go up into the clouds, the real clouds. By the way, how many of you saw the cloud spoof on April 1st from Google? No, all right, a couple of you. Well, you're all nerds. So. Anyway, the idea that in the real cloud, in actual clouds, there's actually organisms that live their entire lives up there. There are microbiomes in the clouds. And wouldn't it be fun and they basically live inside of raindrops. Wouldn't it be fun to build some little doodad that could go inside of a raindrop, and you just throw it up into the air and it would somehow evaporate and find its way into a cloud, and then it goes through the water cycle and lands in some other country. When it lands, it sends out a couple of bursts. You hope there's somebody with a cell phone that has downloaded the app that knows how to listen for the burst. You record where the raindrop fell, and you learn something about the water cycle. Now, I don't know if that's possible, but wouldn't it be cool if it were? Stuff like that. That's what we would like to be able to do. Build machines that can either do stuff or at least go out and report stuff to us in ways that haven't been done before. But we don't know how. None of this exists, or very little of it exists. So my answer to this question is yes, we do want to miniaturize machines. I think it would be really cool and really fun, and will teach us lots of stuff along the way as well. Okay, so that kind of sets the table. Before we jump into how we might go about making small machines, I'm going to say just a word or two about the old nanotechnology, the information technology world. And how did this happen? How were we able to invent a technology that allowed us to make features at the 100 or even 10 nanometer scale? That's what all those zeros are on that integrated circuit up there. If you zoom out to the human scale, which is about a 1 meter, that's equivalent to if you started at the human scale and zoomed out to the size of the planet. Okay, that's how much. So a transistor is as much smaller than you as you are smaller than the planet. Okay, that's pretty good. That's pretty good miniaturization, I have to admit. How did that happen? And there are lots of answers to that question, but I will mention two right now. The first is the idea that information is basically abstract and therefore scale invariant. This is one of the things that Feynman made a big deal out of. I don't care how big the information is, I just want it to be a 1 or a 0. So if you can figure out how to scale everything down, everything's fine, nothing changed. Information size, physical size has no value, just the number of bits that you have. Furthermore, clever electrical engineers figured out a way to take a transistor, scale all of its dimensions, and change the voltages on it so that it functioned in an identical way that it did when it was at a larger scale. So there was a well-defined path. Keep doing this and it will get smaller, but it will still work in the way that you recognize from the larger scale. It was a scale invariant technology, at least down to a very, very small size scale, kind of like renormalization group in physics. And once they had that, they could just follow this path where they just kept making things smaller and smaller, step by step. And that's what gave rise to Moore's law of increasingly shrinking transistors, and set into a pathway a series of doublings in capabilities that just over the course of a few decades completely changed the world. So that's one thing, this scaling. The physicists and electrical engineers call this scaling. Does it work the same when you make it smaller? The second thing, which is perhaps a little less obvious, is listed here, that a very human thing was done reasonably properly, what I've called intellectual property management. Meaning they managed to work together in a way to cause this technology to shrink, and they worked together in a way that was effective. They didn't get mad at each other. They didn't have intellectual property fights like Hooke and Newton did and stop the whole thing dead. They tried. In fact, the inventors of the transistor fought bitterly over the patent rights for the transistor, but it turns out that somebody else had already patented the transistor, so that was all irrelevant. And furthermore, by the time anybody made any money off of it, I think most of the patents had expired. But after that, there was this very collusional way in which the semiconductor industry went about making this technology getting smaller and smaller, probably illegal in certain ways. Which brings us to another, I'm going to, at the risk of this becoming 10,000 Arabian Nights and jumping back to another story, I'm going to jump back to one more. Let's talk about patents for a second, just very briefly. So patents, in principle, are supposed to help innovation, right? You get a patent on something, it gives you enough room to do some work on that and invest time and economic resources in order to make something go with it. In fact, by the way, the first patent was a nanotech patent. That's kind of cool. It was stained glass, which is made up of little tiny nanoparticles. That was quite a while ago. You may say, well, of course, patents, that makes complete sense. Well, patents don't have to be. That's a choice we make, that you can patent an idea. And I mean, you know, if you go into art, right, when Picasso painted the first sort of proto-cubist painting, he didn't patent that, and then no other painter could paint that way for 15 years. No, they started playing with it right away, and it gave rise to an entire school of painting that evolved much more rapidly than it would have had the patents gotten in the way. And in fact, there's an increasing appreciation that if you want to make something go, something that involves putting a lot of technology together in a complex way, you got to get this balance right, this balance between the freedom for everybody to use something combined with the ability of people to protect their patents. And so I'm not going to go into this in any big deal, but basically if everything is open access, you get into trouble because nobody ever invests anything. If you get full exclusion, you get something called the anti-commons problem, that basically nobody can do everything because everybody's got a patent that blocks the thing that you want to do. And the sweet spot is somewhere in between, and apparently the semiconductor people more or less got it right. And you might say, well, of course they did. You know, the patent office, they're full of smart people. I'm sure they got it right. I'm going to disprove that now, okay? How do I disprove that the patent office is not smart? I will show you some patents. This is always fun. My favorite is the first one. There was a patent issued, apparatus for facilitating the birth of a child by centrifugal force. Think about it, all right? There's a diagram over there. This was on the patent. This patent exists. It was granted. I'm not sure if a prototype was ever built. There's another patent. If I had a laser pointer, it's a patent for method for exercising a cat. You shine the little red spot around, the cat chases it. This patent was issued in 1995. It turns out it was issued multiple times. Many people have gotten the patent for using a laser pointer to exercise a cat. And then maybe my favorite of all, this actually wasn't a patent, but was a patent application. It was a patent acquisition and assertion by a non-inventor first party against a second party. What this is a patent of a way to steal other people's patents. And honest to God, it was by an employee of Halliburton. You can't make this stuff up. Okay, I don't know why. Basically, I told you all this patent story because I wanted to tell you about these patents. But, all right, back to our story, back to what I'm supposed to be saying. So we would like to make machines, and you look around you and you see examples of small machines coming left and right, particularly at the sort of milli or hand size. Everybody's seen these cool videos of these little quadcopters flying around, and it's very freaky and weird, but kind of cool too. They've gotten them down to the size of a penny or so. There are smaller MEMS devices like the ones I've shown at right using the techniques from the semiconductor industry, and then there's stuff at even a smaller scale. But let's talk about this stuff, sort of the smallest. I'm going to take a brief aside and tell you about a couple of examples of small machines that are out there now, one very technological and one more scientific. So first, the technological one. So if you look inside of your phone, you might find something that looks a bit like this. This is a MEMS device. It's basically designed that if you shake it, it knows it, or if you accelerate it, it knows it, or if you twist it, it knows it, because of inertia, basically. It's a digital MEMS gyroscope and accelerometer, and it's inside of your phone. And once you have that, I put my phone away, pretend I'm holding my phone, the way that you interact with your phone becomes different, because your phone suddenly begins to live in its world. It's not just an information device anymore. If you tilt it, the screen knows to tilt. Soon, if you move, it will keep track of how many steps you've taken, and you won't need a GPS anymore. It'll just track your motion. These machines begin to take the information technology and make it exist in our reality in a very distinct way than it is the case now. Your phone becomes a part of the world. And this is going to get more and more prevalent. These machines are actually pretty big. If you look in the lower right-hand corner, this thing is sort of a millimeter across, which is, that's small, but from the point of view of nano, it's huge. Now, we do make smaller machines in the laboratory, and I'll give you one example here. This is some work that goes on in my own group. It's possible to make a very simple machine. This machine is basically a guitar. And the only thing that makes it an unusual guitar is the guitar string is made out of a carbon nanotube, which is a 1-atom thick sheet of graphene rolled up into a cylinder that might be, 10 atoms across or something like that. So this thing is about a nanometer in diameter, and in cartoon form, it looks like the thing that you see in the top there, and you can make it vibrate by thumping it or putting electrical pulses on a plate underneath it. That makes it an electric guitar, and you can play it. It plays at a much higher frequency than does a regular guitar. It's not designed for auditory signals. It's designed for electromagnetic ones. It's more like a mechanical radio. We can make it work in the sort of megahertz to gigahertz frequency ranges by choosing the tension and the size of the string. And the reason that people like it is because it is so small, it is very flexible, and has is a very soft spring. So it's a very soft, tunable little nano guitar. And for example, David Compton's group has used this to weigh things, that if atoms absorb onto the nanotube, it makes it vibrate more slowly, just like you took some silly putty and stuck it on a guitar string. In our own group, which made the first one of these, has used it to do various kinds of signal processing. And I was just going to show you the state of the art of these nanotube guitars, and that's done here. We've gotten good enough. Arthur Bernard, a student of mine, really brilliant student of mine, has learned how to pick up individual nanotubes and play the guitar with more fidelity than has ever been done before. So bear with me. This is now talking about one of my own children, so I will wax poetic for a few view graphs and then get back to our main story. Okay, so how does this work? So this is a microfabricated set of tweezers. It's a little set of tweezers that we're going to use to pick up a nanotube. And the way we pick up a nanotube is shown here. Basically, we grow nanotubes, and they're laying around like pickup sticks on the floor. And then we're just going to take those tweezers and scrape them around until one sticks to the end of the tweezers. It's a very sophisticated technology. And what it looks like in practice, so this is looking down in an optical microscope. See those two arms that are coming up? Those are the tweezers. The nanotubes are on that substrate, and you can't see them because they're too small. You can't see something that's that small. But we just start scanning the tweezers around, and the way we know if we've picked up a tube is we're actually running a current out one arm and then back out of the other. And if a nanotube jumps across those tweezer arms, a current will flow through the device. The nanotube is conducting. So once that happens, we say, oh, we've got a tube, and we pick it up. And you may say, I don't believe that you have a tube there. How do you're just telling stories. This is nonsense. But you can do something that's kind of fun. You can just keep turning up the voltage across this. You can keep running a larger and larger current through it, and then something kind of amazing happens. It starts to glow. A single 1 nanometer diameter tube is glowing enough that you can see with the naked eye. We have reinvented the Edisonian light bulb. Thank you. We're a little late, but it's, in fact, I think actually these carbon filament light bulbs are now illegal, right? They're too energy hungry, but don't tell anybody. But you can see it, it's amazing. You can see the light emitted by this tube, and by the way, it means this tube is thousands of degrees. It's heated up to some fraction of the temperature of the sun, which is why it's glowing. By the way, this whole thing is in vacuum. If this was in air, it would turn into carbon dioxide very quickly. Okay, so this proves we have a tube. We can then bring it over to some apparatus like a little gate where we can put voltages on it to cause the tube to wiggle up and down by electrostatic forces. And we can record the current running through the tube, and as the tube moves up and down, the conductance of the tube changes and the current running through it changes. So the tube's current is a measure of its position as it wiggles up and down. It's not important that you understand that in any detail, but this technique allowed us to do something that had never been done before, which is to take our nanotube guitar, pluck the string once, and then it will kind of ring down the way a regular guitar string was. And we were able for the first time to just record that in real time. So this is the current flowing through the tube converted to actual dimensions as a function of time. And so it wiggles up and down and dies out after we pluck it. It's wiggling at sort of microseconds. So it's, again, not audible frequencies, but more like radio frequencies. But you can also, the fun thing is you can also tune the frequency of the plucked sound by either pulling on the tube or applying a gate voltage to pull down on it. So you can tune it the same way you would tune a guitar by changing a knob. And as a result, you can actually play a series of notes. This is, in fact, a series of notes that were played. This is that same data represented as a Fourier spectrum. You don't know what that is, but you'll know what this is. This is it. Now I just divide the time axis by 500, so I make it into the audible range, and this is what you get. So that's the Cornell alma mater played on a carbon nanotube. You heard it here first, folks. And I mean the whole Cornell alma mater played on a nanotube. And there's actually a ton of physics hidden in here. Those of you who are experts will see the frequency shifts a little bit. There's some chirping at high amplitudes, et cetera, et cetera. But you can also, by the way, you can also hear it ringing when you stop plucking it. And that ringing is just thermal fluctuations, the normal Brownian noise of the universe causing the nanotube to vibrate even when you don't pluck it. So you can hear Brownian motion using this device. So that's really fun. And it shows you, we're getting better at making these kinds of simple nanoscale machines. Whoops, you don't want to hear that again. Okay. Okay, so, we seem to be doing pretty well. There's stuff in your cell phone. I made a nanotube guitar. Are we done? And the answer is, of course, no. And what are the problems for continuing to make small machines? And one of the problems, I go back to the view graph I already put up, that says for information, it doesn't matter how big it is. Okay? But that's just not true for machines. Machines are not scale invariant. If you want to build an airplane, it's a different game than building a fly. And if you want to build a fly, it's a different game than working with something at the size scale of a cell, or even more so at the size scale of DNA. The laws of physics do not scale in a very simple way to allow you to design a macro machine and then just scale all the parts down and have it work just the same way when it's small. So it's a much bigger challenge, and you have to do a lot of work at every scale. You also have more functions you're trying to do. You're trying to build a lot more heterogeneous set of machines than just a transistor. So it's also a more complex space. Well, okay, this is sort of an abstract statement. What about a physical realization of this problem? That's shown here. This is flypaper. Now, if you're a human, flypaper is irritating, but not so bad. You touch it and you can pull yourself away from it because you're big. If you're a fly, it's basically all over. You get stuck and you stay stuck. And the technical reason is that your surface area to volume ratio is scaling badly. Stated differently, your muscles are going down like your volume, but your stickiness is only going down like your area, so sticky wins at small scales. So stickiness takes over when you make things small. Stickiness, or more technically van der Waals interactions, or for that matter any other kind of interaction, really become a bugaboo as you make nanoscale machines. There are other problems. I'll call this one the problem of hinges. Everybody who's over the age of 50 and has knees understands the problem of hinges. Hinges are hard to make, and they're hard to make well. And in particular, like even in micro-scale systems, if you look at a hinge, it's a very fancy system with lots of moving parts, and you can imagine taking this down to the nanoscale is not going to be an easy matter. So it's very tough. So we can do it at the milli and maybe even the micro, but what about the nano? How are we going to deal with things at the nanoscale? Well, I think for that, we need to look at biology for hope. So how does biology do it? Well, biology does it in two ways. How does it beat the sticky problem? It beats that because it lives in water. Biology lives in water, and water sort of coats everything, and surfactants in the water coat everything, so that the water is as sticky as you are to yourself, so you don't stick. Okay? In fact, basically all life exists in water. We are, roughly speaking, water balloons with all of our machinery in water, and then there's the skin that allows us to interact with the dry world. Okay? So nano usually is going to be in water. And to get over the hinge problem, it just makes the darn things so skinny that they bend relatively easily. So, and this approach that it takes is just absurd, right? What you do is you encode a series of elements along a string and a DNA or in a polymer, and then it folds itself up into some useful configuration based on the information encoded in the string, and then it goes and does stuff. I mean, if you want to have fun when you have a new grad student join your group, tell them that that's what you want them to build and see what they think. Make this smart string that folds itself up and does stuff. So, what are we going to do? How are we going to copy that? How are we going to do that? Well, then let's go back to Picasso. So Picasso tells us what to do. Picasso said, "Good artists copy, great artists steal." Okay. So, why reinvent the wheel? The wheel has been invented. It's biology. Let's use it. And that has become a very popular approach to doing nanoscale systems. You just are going to hack life. So rather than build life, just hack it. Okay? And I'll just very briefly mention two versions of that. First is DNA origami. Whoop. So the idea in DNA origami is you design a DNA sequence, we're really good at that now, to come together in just the right way. In fact, you make one long strand and then a bunch of staple strands that will staple it together in just the right pattern. It doesn't happen as smoothly as this, but the end result is the same. It will assemble itself into a structure that you chose by choosing the right DNA elements to put together. And this is, roughly speaking, automated to create any old thing you want. One of the first things created were these little happy faces that you see that are about 50 nanometers across, constructed out of DNA strands. And you don't get one when you do it, you get them by the billions in a little beaker. Somebody said it was the most concentrated solution of happiness ever made. That's super cool, right? That's cool. And people are making more complex DNA machines all the time. There's an even more crude approach, which is synthetic biology, where you just go in and reprogram the DNA sequence of an organism, rip out its DNA, and put your DNA in, and go. So it's a viral approach to making nanomachines. And Craig Venter, shown down here, for example, said over the next 20 years, synthetic genomics is going to become the standard for making anything. Craig Venter is known for hyperbole, but there are people that believe it. And okay, all right, we could do that. I mean, what could possibly go wrong with that? Yeah, we just go to another Michael Crichton book, and we know the answer. So there are obvious, hacking something that you don't really understand is often a very dangerous business. So that's a real issue. You just go in and start taking over biological machines. They have their own agenda. They can do whatever they want. It might not go the way you thought. One other thing that's back to this intellectual property game, the biotech industry has not been very successful in many ways. It's been kind of a disaster as a technology. People haven't made nearly as much money as they thought they were going to. And one argument is that they are too far to the right on this graph. They don't play well together. You sequence a particular genome, you try to patent it, or you patent some little thing, and then you hold on to that for dear life instead of forming large patent pools that you share. So it's entirely possible that part of the problem here is strictly a cultural one. They don't have the right culture for working together in an effective way. But even if you solve that problem, I have to say that this is not the approach I signed up for. This is sort of the moral equivalent of having farm animals do your work for you. That's cool, but we signed up to build a nano car or a nano submarine, not to harness life. Okay, so we're getting near the end. Let's try to get back to our original idea. We wanted to build this nanotechnology, but we wanted to keep a lot of the cool stuff from the left-hand side as we tried to take some cool stuff from the right-hand side. So can we do that? What would that look like? Well, let's go back to the inspiration that we had before. The idea here, again, was to take a bunch of elements, lay them out, in this case in a line, and then fold them up into a structure that does what you want it to do. Okay? So we don't know how to do that, but we know how to do something kind of like that. And that's sort of shown here. What if we took a bunch of elements and laid them out in a plane, and then had it fold itself up into some structure? In this case, it's just a little box that would fold itself up when it's cooled and open itself up when it's heated to deliver drugs or a sensor or something like that. And that's really awesome because we know how to make all kinds of really wickedly cool stuff in the plane. All the electronic devices, all the lasers, all this technology that we've invented in the semiconductor world is basically a planar technology. So all we need to do is figure out how to do that other stuff. Well, it turns out that we know how to do that as well. Well, a different group of people know how to do that. And that group of people are people who play around in this world, which is, you might guess, origami. Origami artists have spent a long, long time learning how to take a two-dimensional system and turn it into a really cool three-dimensional object, right? That's what they do. And it's really obvious, right? I mean, everybody knows what this is, right? Yeah, it's completely clear. Yes, that's right, it's an elephant, yeah. Yeah, it's actually a real, origami is actually a deep and fascinating mathematical problem, design problem, however you want to think about it. Inverse problem. If you give me the elephant, I can unfold it and find the pattern. But if you ask me to generate the pattern, it's a very non-trivial question. It's really, really fascinating. And a question, it's sort of the antithesis of normal physics where you try to find the general. What you're looking for here is the specific. What is some very specially weird part of parameter space where if I make the folds, I get something that's cool. One thing that's fascinating about this sort of origami approach to design is that it's appearing all over the place sort of semi-simultaneously. It's taking off at every scale. People are spending a lot of time thinking about how to design everything from solar panels that will deploy in space where it needs to pack into a tight package for launching and then expand into an open thing for deployment, to smart materials that crumple themselves up in interesting ways, to the one on the lower left, which is a stent that you can insert into a blood vessel and then it will expand and open it up. And the one on the right, I'm not sure what that is. But this, you can go to conferences now, and I've been to a couple, and it's super fun, of people that are all the way from architects down to nano people, and we're all dealing with exactly the same problem, how to build intelligent materials that know how to do stuff in response to external stimuli in a very specific way. And it's super fun. And from a more physicsy perspective, the other great thing about origami is that origami scales in the sense that I mentioned before. If you have a sheet of paper, if you and your sheet of paper are a certain size and you can fold it into the structure, and I shrink all of you down, you can still fold it into the structure if you just shrink everything in exactly the same way. Stated differently, the bending stiffness of a piece of paper scales like the thickness cubed, or it scales like one of the dimensions cubed. So you can just scale the whole system down, and it will still work. So it's a scalable technology. So that's really cool. And in fact, if you can scale it, and we already know how to make atomic paper, well, we're all set up for the last little part of my story. Can we take graphene, and can we do origami with it? Can we start to create things out of atomic scale paper? And by the way, this is the work mainly of a grad student who graduated recently in my group, Melina Blees. And I have to tell you the origin of this research, and as a result, much of this talk, was that she was trying to use graphene to make contacts to carbon nanotubes for some semiconductor research corporation thing. It was so boring that we were both just crying. It was destroying her soul, because Melina is half an artist as well as being a scientist, and there was nothing aesthetically beautiful about making contacts to nanotubes. And so we had to invent some project for her that used her full set of talents. And so after playing around for a while, we came up with this idea of trying to do origami with graphene. And it's basically sort of taken over my research group. And I say that to let you know that it's okay to have aesthetics inform your choices. And I think in many cases, it's a very, very good idea. Okay, well, how far have we gotten? Not very far, but I'll show you how far. So first off, graphene is a piece of paper. So what you're looking at here, that's a sheet of graphene, the thing on the right, the slightly darker thing. And that's a giant probe that's going to push the graphene, giant meaning about 10 microns in size. And it will fold up like that. And you can see all the creases, so it's sort of like a piece of rubber sheet or something. You can retract it, and it's kind of amazing. It just goes right back. It's a reversible rubber sheet. It'll crumple and then uncrumple again. It's very, very cool. Very, very neat. So I should mention, by the way, this is done in water with some surfactants. I told you about the sticky problem. We're taking the biological solution here. We've coated everything with water. But so this is the bare material, and then out of this material we can start to do things like I was thinking about doing before. But we've only done the simplest things, but important ones. This, for example, is a graphene hinge. It's a piece of graphene between two panels, roughly speaking, and it just folds like a paper hinge would fold. It's the simplest hinge in the world, and it's super soft because the graphene is super thin, but it's also super strong. You can do this 10,000 times, and the graphene doesn't care. In fact, you may ask how I'm opening and closing the door, and that's shown here. Actually, it's a little hard to see, but if you look very carefully, you see there's a graphene strip there. So I spiked this with the probe and pulled it back and forth like that. And so there's actually a graphene string tied to the graphene door that's being used to pull it open and closed. So you can begin to get the idea that the graphene can be this kind of platform that you can put cool stuff on and then use it to be the guide to fold it up. It's just kind of a background. And you can do more than that. We haven't done any origami, but we've done something called kirigami. Now, kirigami is origami, except you're allowed to cut the paper, so you can cut it. And as a trivial example of what you can make, if you cut the paper like this, you can make a spring. So if you pull on it, it stretches, it opens and closes, and you can make the softness of the spring whatever you want by choosing the pattern of cuts. So again, this is a loop back to our friend Hooke of Hooke's Law. We can make a Hooke's Law spring with any properties you want just by designing a particular cut pattern. Well, does this work? Yeah, so there's your graphene kirigami spring. And you can pull it, and it works just like a regular spring, like the paper version. In fact, Melina, she would design the masks for this. She would walk over to the architecture school. She would cut them with the laser cutters out of paper or vellum, make the model, play with the model, walk to the other end of campus to the CNF, use the same masks to pattern the thing out of graphene, bring them back to the lab, and start playing with them with graphene. And she always kept saying that, you know, it works, meaning what you do with the paper, it feels like what you do with the graphene. And the reason is the kind of scaling that I told you about before. It's very much the same problem. So it's really, really fun and interesting, and just a start. But it does show the kinds of things that you can do. My colleagues in the Gracias group at Johns Hopkins have taken the next step where they'll take a graphene layer with some other polymer that will change if you heat it up or put something in to cause it to swell. And using that, they started to make grippers where it's a graphene sheet with some other stuff that work together to cause grippers. So we're beginning to make more advanced kinds of things that respond to their environment. And, you know, if you project forward, you begin to get the idea of starting with a 2D material that's on a substrate. You pattern a bunch of cool stuff on it the way you want it. Then you set them free in a beaker, and then they can fold and unfold as you desire. And you begin to have these things that have the functionality that you wanted from the left-hand column with some of the mechanical abilities that you had in the right-hand column. And you begin to start to see how you could go about developing this kind of Internet of Things at the micro and nano scale using these sorts of technologies. So we're super excited about this, and you know, this is sort of where we are now, is trying to figure out which kinds of problems we want to attack using this sort of approach. And we're really thrilled, and we want to really try to take our best shot at doing what Feynman asked us to do, which was to build nanoscale machines. And we want to do it for the practical reasons here, but I think we also want to do it just because the idea of trying to learn how to build stuff at the nanoscale, how to make nanoscale machines, will teach us not only about the machines that we're building, but also about, say, biology, because it's faced the same problems, learning how to build nanoscale machines to make us. So in learning about these, we're also learning about ourselves. And that takes me to the Feynman's last little bit of wisdom. This was from his blackboard after he died. And there are two things that I want you to notice. The first thing is he says, I want to know how to solve every problem that has been solved. That's just irritating, you know, that he would even think that he wanted to do that. But the one that I want you to pay attention to is the one above it, which is, what I cannot create, I do not understand. And I think that's very true. I think we'll understand so much more about biology once we build our own nanotechnology. So with that, I will stop and thank you and be happy to take your questions.
There's a microphone down, halfway down either aisle, so if you have a question, please walk up to one of the two microphones.
At the risk of being the first one, real-world problems on a scale of what you can do in the third world that we can't do because we're in the first world. Has that been thought about?
You're saying what kinds of these technologies would be deployable in very economically disadvantaged environments?
Well, in those places where we don't have enough resources to spread around, is nanotechnology going to give us the ability to do things that we couldn't do, just like the information technology has given us those same kind of features?
Yeah, that's a great question. I think the answer is yes, and I didn't go into this a lot, but one of the big shorter-term pushes for these sort of micro-technologies is sort of lab-on-a-chip type stuff, which comes in fancy versions that the healthcare companies can charge you lots for, but also comes in simple versions with little pieces of paper that wick things and allow you to make tests that are very simple. So the idea of extraordinarily simple, cheap, and fast medical tests for all kinds of things is something that is being rapidly developed now and should just get better and better as time goes by. And even, you know, as we found with the electronic stuff, even the sophisticated stuff gets so cheap that it becomes deployable and completely changes the game. You no longer need the same kind of infrastructure in a third world country as you do now, because everybody can just have a cell phone and you throw up a few towers and you're off to the races. So it's a really, I think there'll be a tremendous amount of that. Having said that, again, in the sort of biotech sphere, everything gets more expensive, not less expensive, so we'll see. But I think that's cultural more than technological. Yeah.
Well, if there are no further questions, let's thank our speaker again, and thank you for coming.